Hi everyone, this is going to be a quick video just to review Bode plot straight line approximations. So here on the screen I have some of the straight line approximations that you have in your handout, and the secret to plotting the Bode plot will be to pick the parts of your system that match up with these formats and then plot them accordingly. So the first format we have is if g of s is actually equal to a constant. If it's just a constant, the phase angle is 0 degrees and the gain will be 20 log whatever that constant is. The next very common format is a 1 over tau s plus 1 format. That requires a 1 on top of the equation, some number tau multiplied by s plus 1. So we have to make sure that our equation is in that format. If we do, when we go to plot it, we figure out what 1 over tau is. At that point on the graph, we know the gain will depart from being 0 dB and start to head down the graph at 20 dB per decade. And we know that at that 1 over tau, the angle will be minus 45. If we go a decade, so a division of 10 below 1 over tau, we know that's where the phase angle is going to flatten out at 0. If we go 10 above, we know that's where the gain is going to flatten out at minus 90, and in between we draw a straight line in between. Okay, so looking just at those two, we'll do an example that combines these two. Okay, so we're going to take a look at an example from your worksheet. It's number E, and that equation is 3 over s plus 2. Okay, that's what g of s is. And the thing we notice here is that it doesn't fit our form of tau s plus 1 on the bottom and a 1 on top. So we want to rearrange it until it's in that form. So the first thing I'm going to do is factor out the 3 from the top, and I'm going to get 1 over s plus 2 on the bottom. But I still don't like having that s plus 2. I want it to be s plus 1. So I'm going to divide the bottom by 2, but then I also have to divide the top by 2. So I would end up with 1/2 on the top and 1/2 s plus 1 on the bottom. Okay, and I don't like the 3 and the half sort of being separate because I still want that 1 on top. So I'm going to bring that 1/2 out so that I can get that 1 back on top, and I still have my 1/2 s plus 1 on the bottom like that. If I combine the 3 and the 1/2, I get 3/2 1 over 1/2 s plus 1, and that equals 1.5 times 1 over 0.5 s plus 1. Okay, so I've made my fractions actual numbers there. And that fits two forms from our graphs. You notice we have a constant term out front here, and that fits the pure constant, and we know how to plot that. And this part fits the form 1 over tau s plus 1, and we know how to plot that. And this one here fit that form of k. Now, the thing we have to remember, we have two terms in our G of S that are multiplied together, but because if we have two terms that are multiplied together, we know that we can add their phases, and we know that because the gains are in dB, we can also add the gains. So let's take a little moment to look at why we can add those gains and phases. Remember that when you have two things that are multiplied together that both have a magnitude and a phase, the result has a magnitude that is the multiplication of the two magnitudes, and the phases get added. But we're plotting the gain in decibels. So we're taking 20 log of R1, R2, which is equal to 20 log R1 plus 20 log R2, which is adding the decibel magnitudes of the two gains, and that's why we can add the gains as well as adding the phases. So in other words, we can only add the gains if they're in decibels, and they are. So going back to our equation, we've rearranged it to be 1.5 multiplied by 1 over 0.5s plus 1, and now we're going to plot that on a Bode plot with straight line approximations. We're going to do it by plotting the Bode plot for 1.5, plotting the Bode plot for 1 over 0.5s plus 1, and adding the two of them together. Okay, so I have my Bode plot graph paper in here with dB and degrees. So I've separated the gain and phase parts with this black bar across the center. I have to put the omega scale on myself. First, I'm going to plot the frequency response of G of S equals the 1.5. Now we know that the gain has to be in decibels, so I'm going to calculate 20 log 1.5, and that is equal to approximately 3.5 dB. Okay, now I know that that the phase angle is 0 degrees for all frequencies, and I know that this gain is going to be 3.5 dB for all frequencies, so I could put my labels of 0 and 5 there, and then I can just draw my straight lines. Okay, so I'm going to do this by hand. 3.5 is about here, and it's just going to go all the way across, and 0 dB. Whoa, these are not very straight lines. Is all the way across. Okay, assume those are straight lines. That's where it would be. Now what I'm going to do is I'm going to bring in another plot. Scroll up. So there's my other plot, and this time what I want to plot is, and maybe let's pick a different color. Okay, so this time we are plotting G of S equals 1 over 0.5s plus 1. And for this, the tau is equal to 0.5. When we're plotting it, we want to look at the omega that is equal to 1 over tau, and that would be 2. So I'm going to pick my omega frequency points here. That's going to be 1. That's going to be 0.1. This will be 0.001. Remember, this is semi-log paper, so every major division it's multiplied by 10, and of course the distance between 1 and 2 is the longest gap. So 2 is actually right here. Okay, and the key reason I'm looking at this 1 over tau equal to 2 is in the straight line approximation graph, that is when the gain plot stops being 0 dB and starts dropping at 20 dB per decade. So I'm going to make 0 here, and I'm going to make this minus 20, and of course that would be minus 40. So at 2, that's where it's been at 0 dB, and it's been at 0 dB all the way below that. But then it's going to start dropping at minus 20 dB per decade. So by the time it reaches 20, which is right here, from 2 to 20 on this on the log part of this semi-log, that's called a decade. So by the time it reaches there, it will have dropped by minus 20 dB. And then the next point would be there. So I can connect those with a straight line, and that is the gain plot. For the phase, that 1 over tau or 1 over t point equal to 2 is where I'm going to hit 45 degrees. Or sorry, minus 45 degrees. So I put minus 45 degrees there. Minus 90 is going to be there, and that would be 0. So here at 2 is where I hit minus 45. A decade below is 0. A decade above is 90. Minus 90. So I'm going to make those straight lines, and in between I join it with a straight line. So now I've plotted the two graphs for the two parts of my transfer function. I need to add them up. Let me show the addition of these two graphs on the same graph as the g of s equals 1 over 0.5 s plus 1, but I'm going to show it in a different color. So I'll show it in a bright magenta. And notice that the phase of my red plot here is 0 degree. So when I add that to the other one, it doesn't change it. So the phase for the total will actually end up being unchanged. So I'm going to draw the phase for the total, and it is the same as the phase that's already there. For the gain, 0 dB plus 3.5 dB is going to be 3.5 dB. And when I get to the sloping part, everything goes up by 3.5 dB. So that scale is a little bit larger than this. This one goes 0 to minus 20. So going up by 3 dB is really only going up by about one of these little squares. So every point on here goes up. So that is the 3.5 dB point. And then these points here will also be raised. But that slope of minus 20 dB per decade is still the same. So the purple is the plot of g of s equals 1.5 over 0.5 s plus 1, which is the same as 3 over s plus 2. And if I wanted to verify that in MATLAB, I could type in Bode, round bracket, square bracket with 3, comma, square bracket with 1 and 2, to be the s plus 2 of the denominator, round bracket again, and when I let that command run, it gives me the magnitude in phase. And notice that the MATLAB plot, of course, is not a straight line approximation, so it shows the nice smooth roll off and the nice smooth phase changes.